Engineers play an important role to save our environment. Understanding the chemistry of water is understanding the environment itself. And this is topic 8. Life as we know it will not exist without water. Over 70% of the planet is covered in water. Our bodies is around 70% water. Why is water so important? The structure of a water molecule is capable of making hydrogen bonds with multiple other molecules simultaneously. This provides water molecules with many unique characteristics. Water has the following characteristics. We have universal solvent, cohesion and adhesion, high surface tension, high heat capacity, and changes in density. As a universal solvent, many substances can dissolve in water. It has something to do with the polarity of water molecules. When salt like NaCl is placed in water, the negative ends of a water molecule are attracted to the positively charged sodium ion. The positive ends of the water molecule are attracted to the negatively charged chloride ion. This attraction causes the sodium and chloride ion to break up or dissociate in water. Why is this important? Since our cells are mostly water, these solutions of ions and molecules allow chemical reactions to occur much more frequently, which is an important feature to allow organisms to respond to their environment. Water molecules are also cohesive and adhesive. The hydrogen bonds in water cause molecules to stick together. The property of water molecules sticking together is cohesion. When water molecules cling to other substances, we call this adhesion. Why is this important? Water fills the internal transport systems of plants and animals because of the cohesive and adhesive properties of water. Water allows for the transport of nutrients and waste within an organism. Water also has a high level of surface tension. Because of water molecules at the surface are more strongly attracted to each other. Because of the air above, water molecules cling tightly to each other. The surface tension of water explains why insects float at the surface of water. Water has a high capacity for heat. The many hydrogen bonds that link water molecules let water absorb heat without changing its chemical state. Water's heat capacity stabilizes bodies of water like the lakes and the Carayans. Water's heat capacity plays an important role in the physiology of organisms. Physiology is the branch of biology that deals with the normal functions of living organisms and their parts. Water's heat capacity also helps organisms maintain homeostasis. Homeostasis is the tendency towards a relatively stable equilibrium between interdependent elements, especially as maintained by the physiological processes within organisms. Since life is based on water and the temperature of water rises and falls slowly, living organisms are better able to maintain normal internal temperatures and are protected from rapid temperature changes. The density of water is based on its temperature. Unlike any other compounds which contract when they freeze, the configuration of the hydrogen bonds in water causes it to expand when it freezes. This expansion causes ice to have a lower density than liquid water. That is why ice floats on liquid water. If in case ice would be more dense than water, then ice would sink. Ponds or the carayons and lakes will freeze solid, making life impossible. Bodies of water always freeze from top to down. The ice on the surface acts as an insulator to protect the water below from freezing. This protects organisms so that they could survive the winter. What is an unsaturated solution? A solution that can still dissolve solute. What is a saturated solution? A saturated solution is a solution that contains as much solute as will dissolve at a certain temperature. What is a supersaturated solution? A supersaturated solution is a solution that contains more solutes than in a saturated solution. For an unsaturated solution, you notice that there are solutes that dissolves in water. But if the amount of solute is just enough for water to dissolve, it is a saturated solution. But if more solutes will be dissolved in water more than its normal capacity at a certain temperature, then we call it a supersaturated solution. Let me demonstrate a further explanation on unsaturated, saturated, and supersaturated solution. Let's consider sugar and water. Once sugar is placed in a certain container, and then we place water and stir. After more stirring, you notice that we could not see the sugar crystals anymore. They are dissolved in water. The resulting solution is an unsaturated solution. Why is it an unsaturated solution? Because it still can dissolve more solute, which is the sugar. Let us try to add more solute or more sugar. So we will add more sugar to the water, which is the solvent. We stir, and after stirring, we will still notice that we cannot see the sugar crystals anymore. They are dissolved in water. The resulting solution is a saturated solution, wherein we have just placed or dissolved just enough sugar or solute in water. Since the solution cannot dissolve any more solute, we will still try to add more sugar again. Add more sugar, we wanted to add more sugar, and then we try to stir also. The resulting solution is a saturated solution with additional solute that does not dissolve. If we have solute that does not dissolve, it is more than the capacity of the solvent, which is the water, then the resulting solution is a super saturated solution. However, for a super saturated solution, if we apply heat, tendency is the resulting solution is a saturated solution, because the higher the temperature, the solubility of water increases from a saturated solution, or rather from a super saturated solution, it becomes a saturated solution. After cooling the heated solution to room temperature, the resulting solution goes back to a super saturated solution. We have some additional examples. These are examples of unsaturated solution, like the vinegar. A saturated solution wherein just enough solute is dissolved in a solvent will be the butter. A supersaturated solution wherein we have many sugar forcibly dissolved in water at higher temperature, and suddenly we freeze this or we cool this off, then our soft drinks will be an example of a supersaturated solution where the solute is sugar. Let us talk about concentration of solutions. Concentration is the amount of solute per quantity of solvent. Phenol is a very volatile chemical. High concentrations of phenol can kill. Low concentrations of phenol are components found in certain medicines like antiseptic or disinfectants. Chemists express concentrations of an unsaturated solution as a mass of solute dissolved per volume of solution, similar yet different to solubility. A mass per volume percent gives the mass of solute dissolved in a volume of solution in a percent. So the mass volume percent is the mass of the solute. We divide that by the volume of the solution and multiply 100. A pharmacist adds 2 ml of distilled water to 4 grams of a powdered drug. The final volume of the solution is 3 ml. What is the concentration of the drug in grams per 100 ml of solution? What is the percent in mass per volume of the solution? First thing is to solve for the mass volume percent. This is equal to the mass of the solute divided by the volume of the solution and multiply 100. From what is given, the mass of solute is 4 grams and we divide that by the volume of the solution, which is 3 ml, multiply 100, we get 133%. This is the mass volume percent of the solution. The next requirement is to solve the concentration of the drug in grams per 100 ml. So to solve the concentration of the drug in grams per 100 ml, that is actually 133 grams of the drug per 100 ml of the solution. This is similar and equal to 1.33 grams of the drug for every ml of the solution. What does this mean? It means that for every 133 grams of the powdered drug, it is dissolved in 100 ml of distilled water. Molarity will be the number of moles of solute divided by the liters of solution. If we have a solute, which is sodium chloride, equivalent to 0.75 mole, and the volume of the solution is 4.2 liters, then we could solve for the molarity. 0.75, we divide that by 4.2, we get 0.17857142 moles per liter. This will be the unit of molarity. We also can use molar as a unit of molarity, or just simply the big letter M. What is the molarity of a solution made by dissolving 3.4 grams of potassium permanganate in 5.2 liters of water? First, the mass is given and the volume of the solution is given. However, the mass of the solute is in grams. We have to convert this in moles. So, by looking at the periodic table, potassium is 39, manganese will be almost 55, oxygen is almost 16. We take the totals and we take 158 as the molecular weight of potassium permanganate. Now we are ready to solve for the molarity. So converting grams into mole, that will be 3.4 grams times 1 mole of potassium permanganate is equal to 158 grams. So this will become 0.0215 mole of potassium permanganate. To solve for the molarity, this will be 0.0215. We divide this by the volume of the solution, which is 5.2 liters. So we get here 0.004 molar. There are some problem sets that I had posted here and I want you to solve them, and I'm not requiring you to submit anything at all. It's up to you to solve them so that you could make problems, or you could solve problems easily, as if this will be your practice. If you're not contented, I still give another set again. That will be problem set 2. Try to solve them to understand and solve problems about concentration. So there are many classifications of pollutants in water. They could be toxic, they could become endocrine disruptors, they could be teratogens, mutagens, carcinogens, and neurotoxins. They also could be classified according to what they are, or they're classified chemically. Then we could call them as inorganic pollutants, organic pollutants, radioactive isotopes, gases, including nanoparticles. There are major types of pollutants also in water by what they are, as we had discussed. Chemically, they could become inorganic in the sense that they may be metals or anions. They may be organic, wherein they could be hydrocarbons, they could be PCBs, they could be insecticides and herbicides, they could be pharmaceuticals. If we talk about pollutants like metals, we usually generally have lead, cadmium, copper, mercury, manganese, and more. The metals are actually discussed according to their anthropogenic enrichment factor. Human activity is more important for the availability of anthropogenic enrichment factor. The anthropogenic enrichment factor is used to describe bodies of mineral ore. It is defined as the minimum factor by which the weight percent of mineral in an ore body is greater than the average occurrence of that mineral in the Earth's crust. It can be used to compare the necessary enrichment of the different types of minerals for the recovery to be economically viable. The anthropogenic enrichment factor relates to economic viability, and this is largely determined by the value of the mineral. Second, the level of technology that is available to recover the mineral. The third one will be the cost of refining the mineral ore. And of course, we have to consider macroeconomic factors. If we look into the periodic table regarding our pollutants, we can classify them that our pollutants could be metals. The metals are generally found on the left sides of the periodic table, and the metalloids are somewhat found somewhere in the boundary between metals and non-metals. And the non-metals are found generally on the right side of the periodic table. So inorganic pollutants could be classified. Let's say, for instance, metals, we can have class A. They could be hard metals, but they easily lose electrons to form cations. We can have calcium, potassium, and magnesium. Metals could be inorganic also, and they will be class B, and these are actually soft metals that form covalent bonds and compounds. Metals could also be inorganic, and they could be classified in the borderline, and these are the intermediate metals, which means they have tendencies from both A and B classes. We also have inorganic pollutants like the anions. They are not toxic, but they cause problems, and they could alleviate nutrient limitations. Examples will be our nitrates and phosphates. Pollutants may be organic. If we say organic, these pollutants will contain carbon and hydrogen. There is a question here: which molecule or molecules are organic? Is it A, B, C, D, or E? Okay, you're correct. The answer is B and D. Why? Because glucose and benzene, they contain carbon and hydrogen. CH compounds will also be called hydrocarbons. If only C and hydrogen will be present, then we call them hydrocarbons. Still, they are organic. We can have other compounds also with oxygen, like OH, HCO, NO2, and they are more soluble and more reactive. Other pollutants could be of low molecular weight, they could be of intermediate molecular weight, and they could be of high molecular weight. Propane, at a normal temperature and pressure, propane should be, will it be gas, liquid, or solid? Well, you're correct. It must be gas. For propane, it only has 3 carbons, and it is having a low molecular weight. Hydrocarbons could be also saturated and unsaturated. Most hydrocarbons will be alkanes, are the saturated, and then the alkenes and alkynes will be unsaturated. Hydrocarbons also are classified according to the bonds that they make and the number of carbons that are present in the hydrocarbon chain. For instance, alkanes, there are only single bonds in the chemical formula. If there's only one carbon, it's methane, 2 ethane, until we have 10 carbon in the hydrocarbon chain. Our hydrocarbons also could be aromatic, or they also could become polycyclic aromatic hydrocarbons. They also could become polychlorinated biphenyls or PCBs. Pollutants also could be in the form of insecticides and they are considered organic. Organic in the sense that they also contain organophosphorus. It means it contains phosphorus in the insecticide. These are some examples of insecticides that we see and that we use. Other pollutants that are considered organic could come from pharmaceuticals and from personal care products. So let's review the major types of pollutants in water, may be inorganic and organic, which we have discussed. And there are other pollutants in water like radioactive isotopes, gases, and nanoparticles. For the radioactive isotopes, gases, and nanoparticles, consider them as your assignment. You read more about them.